I think definitions like static friction is one of those things that people overlook, right? People usually concentrate on Newton's first law, second law, third law, so on and so on. But these kind of definitions are definitions that people oftenly overlook. They don't really give themselves some time to actually go through and memorize these kind of definitions. So I'm expecting that a lot of people actually got 2.1 wrong. But anyway, stories. Let's take a look at 2.2. Draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. Right. 2.2. Just like 2.1. People are not paying attention to the details. So I think that this is another question where people got it wrong. But most people think they got it right, but they actually got it wrong. Let me show you why. So 2.2, the key word here is horizontal, right? We want to draw a free body diagram showing all the horizontal forces. So if you include the vertical forces, I'm assuming you'll probably get it wrong, right? You'll probably lose 1 mark for every vertical force that you include. I think that's probably what's going to happen. So if you include the normal force and the weight, I think you're going to get nothing, or at most 1. But I'm quite sure there's no way you get all the marks if you include the vertical forces. So free body diagram for this object. Let's read through the question statement and see what is happening. In an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table. So already we know that we are supposed to have friction, right? Because it acts horizontal. It is connected to a mesh hanger by means of a light inextensible string passing over a frictionless pulley, as shown in the diagram below. Mesh pieces are added to the mesh hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different meshes to increase the hanging mass each time. Ignore the effects of air friction. So right, that is the information we have. And then we're supposed to draw a label free body diagram acting on the crate just before it starts moving. Okay, so obviously we have the tension, right, as a consequence of the light inextensible string that connects the crate and the mesh hanger. And then we also have frictional force, right, acting on the object. So there we go. These are the only 2 forces that we're supposed to have: frictional force and the tension force. Right, no normal force, no horizontal force. Not because they are not there, not because they do not exist. They still do exist, but the question is saying only the horizontal forces. So we have to respect that. And then 2.3.1, we're supposed to calculate the coefficient of static friction. So we are looking for this coefficient of static friction. So we already know fully well that the static frictional force is equals to the coefficient of the static friction multiplied by the normal force. The coefficient of static is usually greater than the coefficient of kinetic. Right. You will see why I'm mentioning that in this question as we do 2.3.2. So what information do we have? Do we have the frictional force? Maybe. Let's take a look and see what we have here. We are actually not given the frictional force, right? The static frictional force. So how the hell are we supposed to calculate it? But do we have the coefficient? The coefficient is what we're interested in. So obviously we don't have that. What about the normal force? Well, the normal force, we can calculate it, right? Because there's no Fy, the normal force is just going to be equals to the weight. So the normal force, 8.5 multiplied by 9.8. So let me just put this in my calculator and see what happens. My calculator is in scientific, so let me put it back to normal. So we have 83.3 Newton. This is the normal force. And then the coefficient is what we're interested in. So how can we calculate the static frictional force? How can we possibly calculate that? Okay, let's take a look at our scenario here. In 2.2, we have a free body diagram, right, of the crate just before it starts moving. Just before it starts moving, the frictional or the static frictional, it is supposed to be, because it's just before it starts moving, should be equals to the tension, right? But how can we calculate the tension? We are given this diagram here, right? You can see that when the hanging mass is 4.2, our crate starts moving, because that's where we start having a bit of acceleration, right? Right here at 4.2. So the static frictional force is equals to the tension, right? But the tension here on the mesh hanger with the mesh pieces is just equals to the weight, right, of that object. So that is, what is the mass of that thing? Let's take a look. The mass is 4.2 when we start having an acceleration, and acceleration due to gravity is 9.8. So we have 4.2 multiplied by 9.8, which is equals to 41.16. So we have the static frictional force. So now we can see 41.16 is equals to the coefficient multiplied by 83.3. So the coefficient is going to be equals to 41.16 divided by 83.3, which is equals to 0.49. So that is 2.3.1. Let's take a look at 2.3.2. We are looking for the magnitude of the acceleration represented by y on the graph if the coefficient of kinetic friction between the crate and the table is 0.4. So take a look at this. The coefficient of kinetic friction is 0.4, and we calculated the coefficient of static friction to be 0.49. So we are quite convinced that the answer we have in 2.3.1 is correct, because if the coefficient of kinetic friction was greater than this one for static friction, we should be worried, because we know fully well that that should not be the case. So there we go. We have the coefficient of kinetic friction, and then what else do we have? We are looking for the acceleration at y. So we do have the mass, we have the hanging mass, right? So the hanging mass is equals to 7.4. Let's concentrate on the crate. If we concentrate on the crate, F net is equals to ma. We know that fully well. And then the force that is pulling the crate is the tension minus the frictional force that opposes. And this is equals to ma, right? So what is the tension? We don't have the tension at this point. What about the frictional force? We have the coefficient, right? So this is 0.4 multiplied by the normal force, which is 8.5 multiplied by 9.4, 9.8, 83.3. So we have 83.3, and then this is equals to 8.5a. So tension minus, so 0.4 multiplied by 83.3, and this is equals to 33.32, and this is equals to 8.5a. Okay, so it seems like we are we are stuck here. We have the tension, we have the acceleration, and we have two variables, right? So we need another equation. So let's concentrate on the mass hanger. The mass hanger, the free body diagram, it should be the weight and the tension, right? So why is it going down? It is going down because of the weight. So weight minus tension is equals to 8.5, not 8.5a, but the mass of the hanger, which is 7.4a. So the weight 7.4 multiplied by 9.8 minus the tension is equals to 7.4a. Okay. Obviously, in place of tension, we can substitute. We can make the tension the subject of the formula in this equation. So it is going to give us 8.5 acceleration plus 33.32. So instead of having tension there, we can say 7.4 multiplied by 9.8, which is 72.52 minus 8.5a minus 33.32 is equals to 7.48. So minus 8.5 minus 7.4, and that is minus 15.98. This is equals to 72.52 minus 33.32. It is equals to 39.2. But when you take it to the other side, it is going to be minus 39.2. So the acceleration is equals to minus 39.2 divided by 15. Is this 15.9 or 15.19? I forgot what that it is, what I wrote there, because it's not clear. So minus 39.2 divided by minus 8.5 minus 7.4. I can just give you that because I'm not sure what I wrote there anymore. So the acceleration that I'm getting is 2.47 meters per second squared. That is the answer to 2.3.2. And here's the question for you, 2.4. A 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the crate? Okay, choose from increases, decreases, or remain the same. Give a reason for your answer. So what is your answer to 2.4? And why are you saying so? Apart from that, let me know which question you want me to do next. Here we go. So I gotta say, I'm quite disappointed because this year there's no free fall or projectile that we need to define. You know, just like we expect in the previous years, we always had one between free fall and projectile. But anyway, stories, let's take a look. So ball A is thrown vertically upwards at 12 meters per second from the top of the building. 2 seconds after ball A was thrown upwards, ball B is thrown vertically downwards at 5.4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time, T seconds. Ignore the effects of F friction like we always do, and then we're given the position time graph for the two balls. Right, so the first question, 3.1.1, we are supposed to, using equations of motion only, calculate the value of each of the following as shown in the diagrams. And then 3.1.1, we are looking for the time t. So t is the time at which the two balls strike the ground, right? So let me just see the mark allocation. It's 5, so it seems like we might need to do a bit of work there. So if I concentrate on ball A, we have an initial velocity. I always take up as positive, so the initial velocity is going to be 12, which is positive. The acceleration is minus 9.8. And then I'm looking for time t, right? It seems like that is all I have as far as ball A is concerned. That is all I have. So with two variables, I'm not going to be able to calculate the time. I need 3 so that I can pick an equation, and then the unknown will be the fourth. Okay, let me try the second ball, ball B. It is thrown downwards at a velocity of 5.4 meters per second. The acceleration minus 9.8. We are looking for time t. So there we go again. We don't have enough variables, but we have two balls. Can we work simultaneously? Can we use ball A and ball B in order to find our time t? Let's give it a try. So if we focus on ball A first, so which equation do we want to use? We want to use an equation that involves delta y. Why am I using delta y? Why am I choosing to take delta y as the fourth variable? Because they are thrown from the same height. So at time t, when they strike the ground, they have the same displacement, right? So for ball A, delta y is equals to vi delta t plus a half acceleration delta t squared. So vi is 12, time is what we're interested in, plus a half minus 9.8, let's say t squared. So delta y will be equals to 12t minus 4.9 t squared. This is as far as ball A is concerned. What about ball B? When we go to ball B, delta y is going to be equals to minus 5.4 t, right? And then plus a half minus 9.8. I know that he's going to give me minus 4.9, but I'm just choosing to write it as it is because I don't want to go to the answer without substituting because I'll lose marks. Well, I'm not going to lose marks, but if you do it, you lose marks in the exam. But anyway, stories. So ball B was thrown 2 seconds after ball B was thrown. So actually, the time t for ball B should not be t. So if you made that mistake, you don't get the answer, right? The time t for ball B is actually t minus 2 because it was thrown 2 seconds later and then it strikes the ground at the same time with ball A. So don't make that mistake. If you make that mistake, then you don't get the answer. I'm sure somebody did make that mistake. And then plus a half acceleration minus 9.8, right? So here we are also going to have t minus 2 squared. This is because it was thrown 2 seconds after ball A was thrown. So delta y is going to be minus 5.5 t plus 10.8. Let me just verify, because in the exam you will substitute 2 multiplied by 2 in the calculator because you don't want to make any mistake. So this is 10.8 and then minus 4.9 and then we have t minus 2 squared, right? So that is going to be t squared minus 4t plus 4. Yeah. If you don't see why that is the way it is, you probably got the question wrong either way. Okay, delta y will be equals to minus 5.4t plus 10.8 minus 4.9 t squared. So 4.9 multiplied by 4. So this is plus 19.6 t, right? And then what? Minus 4.9 multiplied by 4 again. So plus 19.6 t. Is it plus? No, it is minus, because we have minus multiplied by plus. So we have minus. So let's just verify here, because it seems like there's a lot going on. This is fine. This is fine. T squared minus 4t plus 4. This is fine. Minus 4t squared is fine. Plus 16t is fine. And then here we're supposed to have minus 19.6, not minus 19.6t. So, okay, that was another mistake. Yeah, it's always important to verify. So, delta y, so let's add the like terms. So, minus 5.4 plus 19.6, right? That gives me 14.2. So, we have 14.2t. And then 10.8 minus 19.6 minus 8.8. So minus 8.8, and then minus 4.9 t squared. It does not have a like term, so minus 4.9 t squared. So we can equate these two things, these and these. We can equate those because they are both equals to delta y. So 12t minus 4.9 t squared is equals to minus 4.9 t squared plus 14.2t minus 8.8. Okay, let me just verify. Yeah, this is fine. 12t minus 4.9t squared. Okay, that is fine. So obviously we have minus 4.9t squared plus 4.9t squared, right? So we can just drop that. So we're left with 12t is equals to 14.2t minus 8.8. Okay, so 12 minus 14.2, I'm getting 12 minus 14.2, I'm getting minus 2.2. So minus 2.2t is equals to minus 8.8. So t is equals to, so 8.8 divided by 2.2, I'm getting, what do I get? 8.8 divided by 2.2, I'm getting 4. So time t is 4 seconds. So this takes 4 seconds. Okay, there we go. That is 3.1.1. It's a lot of work, to be honest. Yeah, 3.1.1. It's a lot of work. What about 3.1.2? We are looking for the value of z. So z is the height from which the two balls were projected, right? So we, how many marks? 3. Not sure it's worth 3 marks. Okay, but either way, delta y is equals to, we can take one between the two equations. Let's take 12t minus 4.9t squared, right? And then we know that t is equals to 4 when the two balls strike the ground. So when we substitute here, we shall get delta y, which is z. So 12 multiplied by 4 minus 4.9 multiplied by 4 squared is equals to, so 12 multiplied by 4 minus 4.9 multiplied by 4 squared. This is minus 30.4. So z is equals to 30.4, right? It is in meters, right? But z is just going to be 30.4. Yeah, because the meters is here in position, right, on the brackets there. But yeah, the two balls are projected 30.4 meters above the ground. Okay, what about 3.1.3? We are looking for the value of y. So y is the maximum height reached by a, right? So if I still remember a, the initial velocity is 12, the acceleration is minus 9.8. Maximum height, we know that vf is equals to 0, right? And then we are looking for delta y, right? So let's do that. Vf squared is equals to vi squared plus 2a delta y. So we have 0 squared being equals to 12 squared plus 2 minus 9.8 delta y. So delta y is equals to minus 12 squared divided by minus, well, 2 multiplied by minus 9.8, right? So delta y is equals to, so 12 squared divided by 19.6. This is 7.35 meters, right? But y is not going to be 7.35 meters, right? Y is going to be equals to 30.4 plus 7.35. I know we just lost some people there. I know somebody didn't add the two numbers. So y is equals to 37.75 meters. So there we go. That is the value of y. And then 3.2, we are supposed to, on the same set of axes, sketch the velocity time graphs for ball A and B while they're in free fall. Okay, so let's do that. Well, let's have our axis first, right? That's V, that's T. So T in seconds, V in meters per second. So the initial velocity of ball B is 12. So 12, I'm taking up as positive. And that of B is minus 5.4, right? We know that the time T here, we can just put it as T, but we know fully well that it is 4 seconds. Okay. And then the second ball is projected 2 seconds after, right? B is projected 2 seconds after. So here we have ball A. Ball A starts there. And then ball B will start somewhere here, which is 2 seconds after. So what happens to ball A? Ball A reaches maximum height after some time. And then it goes on to strike the ground at time T. Yeah, which is somewhere there. And then what? Let me just draw a straight line here. On the same set of axes. Okay, the question says sketch, so I wanted to ask if you had a graph paper, but I don't think you had. Okay, so I'm putting those dotted lines there so that I can be as accurate as I can be, right? So that is for ball B, and then for ball A rather. Ball B is projected downwards, so it starts here and then stops at time T. So you're supposed to have something like this as far as the velocity time graph is concerned. So there we go. Write down the principle of conservation of mechanical energy in words. That is 4.1. So usually, if in 4.1 I'm defining the principle of conservation of mechanical energy, I'm assuming that in 4.2 I'm going to have to use that principle. Usually it is the principle of conservation of linear momentum, and then we would use it in the equation that follows, right? But here we have the conservation of mechanical energy. So I'm expecting that that's what we're going to use in 4.2. But let's go ahead and see if that is actually the case. So we have two trolleys A and B of masses 1.5 kgs and 2 kgs. And then they're stationary, and then between the two of them there's a compressed spring, right? The trolleys are released and the spring takes t seconds to return it to its natural length, right? The spring then falls to the ground. Trolley A moves to the left while trolley B moves to the right. We can clearly see here after the spring is released. Trolley A then moves to the left while trolley B moves to the right, and then trolley B goes up a frictionless inclined plane, rising to a maximum height of 1.5 meters as shown in the diagram below. So 4.2, calculate the speed of trolley B at the bottom of the inclined plane. Okay, so let's see what we can do here. So obviously the first thing that we're going to try out is the conservation of mechanical energy. If it doesn't work out, then we can try other things. But the most organic step should be the conservation of linear momentum, of mechanical energy, not linear momentum. So let's take a look at the cart B. Is it a cart? No, it's a trolley. So let's take a look at B at the bottom of the incline, and then also take a look at it at the top of the incline. So at the bottom of the incline, that is where we are interested in its velocity, right? Let me just say V and not VF. So we are interested in this velocity at the bottom of the incline. But what else do we have? We just have the mass. That's all we have, right? The mass is 2 kgs. And then at the top of the incline, so the question says that does it reach a maximum height? That's what I want to see, because if it reaches a maximum height, I know that the velocity is 0 there. So it rises to a maximum vertical height. So okay, v is equals to 0 at the top, because that is the maximum height. The mass is still the same, but we have the height, which is 1.5 meters. Here we can say that the height is equals to 0. So this information looks like it is enough for us to use the conservation of linear momentum. We know that the mechanical energy, the total mechanical energy at the bottom should be equals to the total mechanical energy at the top. This is because our track does not have any friction, right? It is frictionless. So we can use the conservation of mechanical energy. So at the bottom, we're going to have EP plus EK, right? Potential energy plus kinetic energy. At the top, we're also going to have EP plus EK. So what is the potential energy at the bottom? We know that the potential energy is mgh, right? So the mass is 2, gravitational acceleration is 9.8, the height is 0. What about the kinetic energy? Half, mass is 2, v squared. That's what we're interested in, right? And then at the top, mechanical energy is 2, 9.8, the height is 1.5. But the kinetic energy at the top is actually equals to 0, because we know that at the maximum height, the velocity is 0. So we have 0 squared there. So this gives us 0, 2 divided by 2 is 1. So we have v squared being equals to. This gives us 0. So let me just put that in my calculator. 2 multiplied by 9.8 multiplied by 1.5. 2 multiplied by 9.8 multiplied by 1.5. That is 29.4. So we have 29.4. So v is equals to 5.42 meters per second. The question says speed, so we don't have to give any direction. We can just leave it like that. Okay, and then 4.3.1. For the t seconds that the spring takes to return to its natural length, calculate the change in momentum of trolley B. Change in momentum of trolley B. So change in momentum delta P, which is m multiplied by Vf minus Vi. We can use this to find the change in momentum, right? So let's see. Before the spring is released, the initial velocity of both trolleys A and B is 0, right? And then after the spring is released and then it is at its full length, B is climbing up the incline with a velocity of 5.42 meters per second to the minus 1, right? Up the incline to the right. Okay, so we are looking for the change in momentum. Well, momentum is a vector, so we need to decide on a direction. Let's take direction to the right, it's positive, right? So we're going to have delta P being equals to the mass 2. Vf is 5.42. Vf is 5.42, right? Minus Vi. Vi is 0, right? Vf is not 0. Vf is 0 there at the top. Here we have 5.42 and here we have 0 once more, right? So don't confuse, don't take, well, 5.42, it's our Vf when the spring is lengthening, and it is our Vi when we are going up the incline, right? So most people, they sort of confuse the two, right? So 2 multiplied by 5.42, this is equals to 10.84. So kg meters per second to the right. To the right. This is the change in momentum of trolley B. While trolley A, write down the change in momentum of trolley A, that is 3.2, right? So it is going to be the same. It is going to be the same, but in the opposite direction, right? It's easy to prove because we know that F net is equals to delta P over delta T, right? So this A and B will experience the same force. We cancel time and time. We end up with delta P being equals to delta P, but in the opposite direction because of Newton's third law. So the change in momentum of ball A, or trolley A, not ball A, will be 10.84 kg meters per second. Where? To the left. All right. Maybe what we can talk about is the SI unit here. The question is saying change in momentum. It is not saying impulse. So should the SI unit be kg meters per second, or should it be newtons multiplied by second? Which one between the two? Kg meters per second or newtons multiplied by second? Right. I think the impulse, right, will be kg meters per second, but the change in momentum will actually be newtons multiplied by second. So let me know in the comments, which SI unit did you use? Did you use kg meters per second, or did you use newtons multiplied by second? I think that is another thing that we need to figure out here. So I'm interested in your answer for this question. Is it in kg meters per second, or is it newtons multiplied by second? And why are you saying so? Right. Again, I think this is one of the things that probably there's going to be a lot of disagreement on. Do we use both? Do we have the freedom of choice? Are we supposed to use one? Let me know in the comments. All right. And then 4.4, calculate the speed of trolley A after t seconds. So now we can use, because we know here we have 0, 0, here we have 5.42, and here we have an unknown speed. So that is the speed that we are looking for. We can obviously use the conservation of linear momentum. So the conservation before should be close to the total momentum before, right, should be close to the total momentum after. Right. So before we have 1.5 plus 2, because, well, we can even separate them if you want that. We have 1.5 multiplied by 0 plus 2 multiplied by 0, right? And after we have 1.5 multiplied by v plus 2 multiplied by 5.42. Okay, so 0 is equals to 1.5 v, and then 5.42 multiplied by 2, not 1 point something. So 0 is equals to 1 point, I've already written it there. So here I'm supposed to have plus 10.84. V is equals to 10.84 divided by minus 1.5. This is equals to minus 7.23 meters per second. So we're looking for the speed. So let me just say 7.23 meters per second and not worry about the direction. There we go. Define the term work done by Air Force. Well, I have to agree. In this exam, the definitions are quite brutal. In question 2, we are defining static friction. In question 3, we don't have a definition. In question 4, we are defining the conservation of mechanical energy. And in question 5, we are defining work done by a force. What? I can't even remember the last time I came across a question and we had to actually define work. But here we go. That's what we're supposed to do. That is 5.1. Let's take a look at 5.2. Draw a label free body diagram showing all the forces acting on the crate as it moves. At least in 5.2, we're supposed to draw a free body diagram showing all the forces. Because in question Q, we're supposed to draw a free body diagram showing only the horizontal forces, not vertical forces. Right? You include the vertical forces and you probably lose some marks. Okay, so let's read the questions. Let's go through the question statement and see what is happening. A constant force F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kgs that is initially addressed as shown in the diagram below. Easy to see. A constant frictional force of 10 Newton acts on the crate as it moves from rest at point A along a horizontal surface to point B. The distance between point A and point B is 1.5 meters. The speed of the crate at point B is 2 meters. So we have 2 meters per second there. Okay, so we need a free body diagram for the crate. And the mark allocation is 4 marks. So first things first, we need the weight, right? We put the weight first and then we think after, right? Because we know that the weight is going to be there. So that arrow there, we're going to put the weight. And then we have the normal force, obviously, because it is resting on a surface. And then we have the applied force, which is at an angle. Do we have a frictional force? Yes, we have a constant frictional force. So I think that is all the forces that we need. Okay, so we have the force applied. We have the weight, normal force, and the frictional force. So 4 marks, 4 forces, seems like we're good to go. Let's take a look at 5.3. Use energy principles, using only energy principles, calculate the magnitude of force F, that is for 4 marks. Okay, so let's see. We have a free body diagram. We have the velocity at A, which is 0, and then we have a velocity at B, which is 2 meters per second. So because we are given the velocity at A and the velocity at B, it seems like we should be able to use the work energy theorem, right? Which says that work net is equals to the change in the object's kinetic energy. Right, but this can work, and work non-conservative should also work. Yeah, I can see that it is also going to work. But if we use work net is equals to the change in the object's kinetic energy, right? But it is also equals to the work, right? The summation of all the works done by the individual forces. So the frictional force does some work on the object, and the horizontal component of the applied force also does work on the object. So we're going to have the work done by the frictional force plus the work done by the horizontal component of the applied force, being equals to the object's change in kinetic energy. So the work done by frictional force is going to be Fr multiplied by delta x multiplied by cos of 180 plus the work done by the horizontal component of the force applied. So that is Fx delta x cos of 0. It's cos of 0 because the object is going from A to B, right, which is the same direction as the horizontal component of the force applied. And this will be equals to half mvf squared minus a half mvi squared. So let's go ahead and substitute. Frictional force is constant at 10 newtons. So we have 10 multiplied by the displacement 1.5 cos of 180. Now let's come to the horizontal component of the force applied. Obviously, because it is a flat surface, it is going to be F cos of theta, right? So we have F is what we are looking for, and then cos of 30 degrees, right? This is the horizontal component of the applied force, and then multiply by delta x, which is 1.5, and then cos of 0 because they're in the same direction. This is equals to a half. The mass of the object is 6 kgs, so we have 6 vf squared. Oh, we have all these velocities. So vf is 2, right? So 2 squared minus a half. The mass is 6. The initial velocity is 0 squared. Okay, so 10 multiplied by 1.5 multiplied by cos of 180. This is minus 15. So we have minus 15, and then cos 30 multiplied by 1.5 multiplied by cos of 0. This is plus 1.299f being equals to, so right hand side 1 over 2 multiplied by 6, 2 squared, minus 1 over 2 multiplied by 6, 0 squared. This is 12. So 1.299f is equals to 12 plus 15, which is 27. So this is 27. So F is equals to 27 divided by 1.299. So F is 20.79 newtons. Right, we only need the magnitude, we don't need the direction. So that's it. So let's just verify and see if what we did is correct. This is the constant frictional force. This is the right displacement, cos of 180 minus 15. Seems good. Cos 30, maybe I can just substitute that in my calculator. Cos 30 multiplied by 1.5, that is 1.299. So I'm happy with this, right? And then 6 divided by 2, that is 3, 4, that is 12. 12 plus 15, yeah, seems good. So that is the applied force. Okay, and then 5.4, I want you to tell me the answer to this question. What did you write? A 2 kg block is placed in the crate. What effect will this have on the work done by the same force? when the crate is again moved from point A to point B, right? Only increases, decreases, or remain the same. So is the work done by the applied force going to increase or decrease when we add the 2 kg block on the crate, or is it going to remain the same? Let me know in the comments. Here we go. Name the phenomenon that explain why the wavelengths shown in the graph differ. I think all the time in question 6, when we come across something like this, we know what the answer is already. Doppler effect. And then question 6.2 is the car moving towards or away from the listener. Give a reason for the answer. Now we have to go through the question statement. A stationary listener standing on the roadside records the wavelength of the sound emitted by a siren of a police car traveling at a constant velocity. In the wavelength time graph below, not drawn to scale, wavelength of the listener is the, wavelength with the subscript of L, right, is the wavelength of the sound recorded by the listener, while the one with a bit of an S here is the wavelength recorded by, the wavelength of the sound emitted by the siren. And then we're supposed to take the speed of sound in air as 343 meters per second. So is the car moving away or towards the listener? The listener is stationary. So what is influencing the wavelength that the listener observes is the motion of the car, whether it is moving away or towards. So take a look at this. The frequency of the listener, or not the frequency, but the wavelength observed by the listener is greater than the wavelength observed by or emitted by the sound source. But wavelength and frequency is inversely proportional to the wavelength, right? So this simply implies that the frequency emitted by the source is greater than the frequency observed by the listener. So if the frequency observed by the source is if the frequency emitted by the source is greater than the frequency observed by the listener, what does that imply? It implies that the listener has to be moving away, given that the sound source is stationary. So that is the answer to 6.2. And then 6.3.1, calculate the frequency of the sound emitted by the siren. Well, we have the wavelength of the sound emitted by the siren, so it should be quite easy to calculate the frequency. F is equals to V divided by the wavelength. We are told that we are supposed to take the speed of sound in air as 343 meters per second. So we have 343 divided by 0.38. It's already in meters, so we don't have to change anything there. So 343 divided by 0.38, this gives us 902.63 hertz. This is the frequency emitted by the source. 6.3.2, magnitude of the velocity of the car. That is actually the last question in question 6. So we are looking for the velocity of, the car. Is the listener the one who is stationary, or the car is the one that is stationary, our sound source? Let's go through our question statement again. A stationary listener. Okay, so the listener is stationary. So the listener is stationary. It is the car that is moving away, right? So the answer here is still away, but it is actually the sound source that is moving and not the listener. The listener is stationary. It's the sound source that is moving away. Okay, so magnitude of the velocity of the car. So this is the velocity of the sound source that you are looking for. We have the frequency of the sound source because we have calculated it. We have the velocity of, the speed of sound in air. It is given to us. Velocity of the speed of sound in air, it is just V. It is given to us, right? Magnitude of the velocity of the car. So we are looking for Vs. We have VL because the listener is stationary, which is 0. And then what about the frequency observed by the listener? We can calculate that because we are given the wavelength, right? Not the we are given the wavelength, but we can calculate the frequency. It is gonna be equals to 340. Okay, let's leave that for now, but we can calculate it, right, as we move forward. So with these variables, we can say FL is equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. So FL, the frequency observed by the listener. So we're gonna say 343 divided by the wavelength, right, which is 0.4. So this is the frequency observed by the listener. And then we have V, which is 343. The listener is stationary, so plus or minus 0. And then we have 343 3. The sound source is moving away, so we're gonna have plus Vs multiplied by the frequency emitted by the sound source, which is 902.63. So 343 divided by 0.4, this is 857.5, and it is equals to 343 divided by 343 plus Vs multiplied by 902.63. Let's divide both sides by 902.63. If we do that, we're going to get 0.95 being equals to 343 divided by 343 plus Vs. Let's cross multiply. So 0.95 multiplied by 343, this is 325.8506, right? And then plus 0.95 Vs. This is equals to 343. So Vs is going to be equals to 343 minus 325, 32, not 3, 32.5. 325.8506, everything divided by 0.95, the coefficient of Vs, right? So let me just put that in my calculator and see what I get here. I'm getting 18.05. So Vs is 18.05 meters per second. There we go. That is question 6. So we have done question 2, 3, 4, 5. If you haven't watched that, click on the channel and you'll find those videos. Which question do we go to next? Let me know in the comments. Here we go. Calculate the magnitude of the electric field at X. Let's go ahead and take a look at that. So 7.1, P is a 2 nanocoulombs point charge, as we can clearly see, right? X is a 0.6 centimeters away from charge P, as shown in the diagram below. We just want the magnitude of the electric field at X. Should be an easy question to answer. So 7.1 E is equals to KQ divided by R squared. So K is 9 times 10 to the power 9, right? It's a constant. But because I'm writing the final exam and I don't want to make any mistake, I will actually verify on the formula sheet, right? Because what if it's minus 9? Well, it is still plus 9. 9 times 10 to the power 9 multiplied by the charge of P. It is 2 times 10 to the minus 9, not minus 6, right? And then divided by R squared, which is in centimeters. So we need to convert to meters. So in 1 meter, we have 100 centimeters. So we divide by 100 and we square that. Now I just need to press my calculator. So 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9, 6 over 100, and we square that. I get 5,000. So we have 5,000. What is the SI unit? We know that E is equals to F over Q, right? So the SI unit is newtons per coulomb. That is 7.1. Let's take a look at 7.2. Point S with a charge of minus 2 nanocoulomb is placed 4 centimeters away or to the right of charge P, as shown in the diagram below. Draw a resultant electric field pattern due to charges P and S. Okay, so P is positive, S is negative. Okay, so they will attract. So what are we expecting? Let me just do that again. We're expecting the charges, well, not the charges, but the field lines to be pointing away from charge P and pointing towards charge S, as S is negative, right? And then let's just go ahead and have some more field lines, right? So they're pointing towards the positive sphere and they point away at the negative sphere, right? So we have something like this. Yeah, actually P is positive and S is negative. we expect the filled lines to point away from P, right? Because it is positive, and point towards S because it is negative. Okay, so let me just write that nicely. So these charges are supposed to point away from P. Let me just add all the filled lines that I'm going to use here, and then I'll worry about the direction after, right? So the filled lines are pointing away from the positive sphere. So this is what away looks like, the point away from the positive sphere. And then the negative sphere, the point towards the center, right? The point towards the negative sphere. So the positive sphere away, and then from the negative sphere's point of view, it is towards. So this is what we're supposed to have for 7.2, right? 7.3.1, we're supposed to define Coulomb's law. So I'm gonna leave that to you, right? The square distance between the charges, not between them, not between their centers. When it comes to Coulomb's law, we don't say between the centers. That is gravitational law. So if you did say between the centers here, when you at the end of the definition, that is wrong. It's not between the centers. It's just between the charges, right? We don't talk about the center of a charge here. So that is 7.3.2 or 7.3.1, I mean. And then 7.3.2, what is the polarity of charge T? Choose from positive or negative. Let's go through the question statement and see what is happening. A third point charge T is placed 2 centimeters to the right of S as shown in the diagram below. Point charge T experiences a net electric field force of 2.5 times 10 to the minus 4 newtons to the left. Okay, to the left. And then we're supposed to figure out whether it is positive or negative. So let's take a look at the two cases where it is positive, right, and where it is negative. Okay, so if it is positive, S and T will be attracting, right? So this will be the force as a consequence of S, because S and T will be attracting. But what about the force as a consequence of P? P and S have the same magnitude, but because P is so far away, we expect the vector to be smaller. We expect the magnitude of the force as a result of P to be smaller. This is if T is positive, right? Let's take a look at when T is negative. If T is negative, this will be the force as a result of S, because they will be repelling each other. But because P has the same magnitude as S and is far away, this makes sense to be the force as a result of P, right? So in this case, when we look at our situation, what do we have? We know that the net electric force is to the left, right? So it means that at T, we have a positive charge because the resultant is to the left when T is positive. As you can clearly see here that Fs would be greater than, here Fs would be greater than Fp. So it is easy to see that at point T, we should have a positive charge, right? Because if it is positive, then the net electric will be to the left. And then 7.3.3, we are supposed to actually calculate the magnitude of charge T. Let's go ahead and do that. So F net will be equals to, this is our scenario, right? We are basing everything on this scenario. So Fs will be equals to Fs minus Fp. I'm taking direction to the left is positive here, right? So what is F net? F net is 2.5 times 10 to the minus 4. What is Fs? Fs is going to be, we'll know fully well that F is equals to K Q1 Q2 over R squared, right? And we want the charge at T. So Fs is going to be 9 times 10 to the power 9. The magnitude of the charge S, 2 times 10 to the minus 9, multiplied by Qt. Everything divided by the distance between S and T. It is 2 centimeters. So 2 over 100, converting it to meters squared, right? And then minus 9 times 10 to the power 9, 2 times 10 to the minus 9. That is the charge of P, right? Magnitude of the charge, rather. And then we have Qt divided by the distance between the two spheres. So it is 4 plus 2, which is 6. So we have 6 divided by 100 squared, right? So if we take a QT as a common factor on the right hand side, we're going to have 2.5 times 10 to the minus 4 being equals to, let me just make this a little bit bigger, right, being equals to, so I'm taking QT as a common factor, right? So we are going to be left with 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9 divided by 2 over 100 squared minus 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9. Everything divided by 6 over 100. 6 over 100 squared. If we divide both sides by this coefficient of QT, we get QT being equals to 6.25 times 10 to the minus 9 coulombs. There we go. 8.1, define the term power. Finally, a definition that you're familiar with, right? It is the rate at which work is done. That is power. P is equals to W over delta T, the rate at which work is done. That is 8.1. Let's take a look at 8.2. So 8.2, if both light bulbs operate as rated, calculate the reading on ammeter A2. So let's go ahead and take a look at our question statement. L1 and L2 are two light bulbs that have the following ratings. We have the power and the voltage of L1, the power and the voltage of L2. The two bulbs are connected as shown in the diagram below. The battery has an internal resistance of 0.6 ohms, while the conducting wires and the ammeters have negligible resistance. R1 and R2 are resistors. Back to the equation 8.2.1, we want the reading on A2. So the bulbs are operating as rated. That is very important. That is information that basically unlocks the equation. What does that mean? It means that the power dissipated by L2 is that which is rated, right? It is that which is given to us, 48 watts. So that is what's going to allow us to find the reading on A2, right? Because we know that the current that passes through A2 is the current that passes through L2, because they are on that same parallel path. So what is the power of L2? It is 48 watts. And then what is the voltage of L2? Voltage dissipated by L2, that is 32 volts. And then what we're looking for, the reading on A2, so that is the current, right? So with these three variables, how do we calculate the current? We know that P is equals to V multiplied by I. The power is 48 watts, right? The voltage is 32, and then the current, well, 32, not 3V, 32, and the current is what we're interested in. So I will be equals to, so 48 divided by 32, that is 1.5. So we have 1.5 ampere as the reading on A2. 8.2.2, we want the reading on A1, right? The reading on A1, the reading on A1, right? So we need to understand the current that A1 reads. The current that A1 reads is the total current, right? So A1, essentially, we are looking for IT. But take a look at this. When the current divides at this point, a proportion of the current is going to go on this path, while the other proportion of the current goes to this path. So if we calculate the current that passes through L2 and the current that passes through L1 and add those two, we have the current that is read by A1, the total current. So the current that is read by L2, let's call that I2. We calculated it to be 1.5 ampere. Let's calculate the current that is read by, not that is read by, but that passes through L1, because there is some current that passes through L1. If we can find a way to calculate the current that passes through L1, we will have the total current, because L1 is also operating as rated. So what information do we have as far as L1 is concerned? Well, we have the power, which is 36 watts. We have the voltage, which is the potential difference, which is 20 volts. So P is still equals to V multiplied by I. The power is 36. The voltage is 20. We are interested in the current. So the current is going to be equals to 36 divided by 20, which is 1.8 ampere. So this is I1, right? I2 is 1.5. So the reading on E1 will be equals to 1.5 plus 1.8. So this is 1.5 plus 1.8. Let's see, supposed to be 3.3, right? That is what we're getting, 3.3 ampere. But we're in the final exam. We don't want to make any mistake. We will literally punch in the calculator 2 multiplied by 2, even though we know that it is 4. So that is 8.2.2. Let's take a look at 8.2.3. So 8.2.2 said, let's find the reading on A1, right? And A1 is the total current. I was just making sure that I didn't miss anything. 8.2.3, the resistance of R1. We are looking for the resistance of R1. Okay, so how can you find the resistance of R1? We have the resistance of R2, which is 4 ohms, right? And then what else do we have? We have the, okay, we don't have the EMF, but we have the internal resistance, and we have the total current. So the total current, we know that it is equals to 3.3 ampere. So can we use the total current to find the resistance of R1? Yes, we can. How? I'm glad you asked. We know fully well that VP is equals to IT multiplied by RP, right? So do we have VP? Because if we have VP, we can easily then calculate the resistance on R1. Okay, so let's see. Let's take a look and see if we can do that. We know the voltage that is dissipated by R2, right? But do we know the voltage that is dissipated along the two parallel paths? Well, we can calculate VP using we can calculate VP using the voltage across this path, right? Because think about it, we say that in series there's different potential differences, right? That's in series, but in parallel the potential difference is the same and the current differs. So VP can also be equals to the voltage that is dissipated by L2. VP is equals to the voltage that is dissipated by L2. It is equals to 32 volts, right? So the voltage across this path, right? Let's call this path X, and the voltage dissipated across the path Y, they should be the same, right? But we already know that, so we're saying that V of R1 plus V dissipated by L1 should be equals to VP, right? Because R1 and L1, that's the only two spots where there's voltage being, there's a potential difference, right? So V of R1, we can calculate that because we know V of L1. V of L1 is 20. So we have 20 being equals to 32. So V of R1 is equals to 12, right? 32 minus 20. So there we go. So V of R1 is equals to 12. But we know the current that passes through R1. So V of R1 can also be equals to I multiplied by R. So V of R1 is 12. We know the current that passes through R1. We calculated it in 8.2.2. It is, so let me see, 8.2.2. It is, so let me check, 36, that is for R1, for L1, and then 20 volts. The current is 1.8. So 1.8 passes through R1. So the current is 1.8 and then multiplied by R. So R is equals to 12 divided by 1.8. This is 6.67 ohm, right? So the resistance across the path at the top Oh, okay, we don't have the resistance of L2, but we don't need to calculate it. So this is one way you can use to calculate the resistance of R1. But already you can see that when I'm trying to solve this problem, there's a couple of ways that are presenting themselves. So if you use a different method and you still got 6.67 ohms, you're still good, because clearly there's a couple of ways we can use to actually answer this question. And then 8.2.4, we are looking for the EMF. So 8.2.4, we are looking for the EMF. So we should be able to calculate the EMF directly because we have everything else but the EMF. EMF is what we're interested in. Internal resistance, we have that. Total current, we have that. External resistance, do we have that? That's what we need to calculate, right? So RS is equals to 4 ohm. We only have one resistor which is in series, which is R2. And then RP, okay, so RP is equals to, I don't like using this one actually, I like using 1 over RP for some reason. It's equals to 1 over R1 plus 1 over R2. So 1 over RP is equals to 1 over the total resistance on one path. The total resistance on one path. Okay, so it seems like we actually do have to calculate the resistance on L2 and L1. We don't have a choice anymore. Okay, that is one approach. One approach can be calculating the resistance of L2 and L2, of L2 and L1, and then calculate EMF using EMF is equals to IT multiplied by R external plus R internal. But another way that is becoming apparent to me and seems easier is if we say EMF is actually equals to V internal plus V external, right? So V internal is equals to current multiplied by the small r, right? Current multiplied by the small r. We have the current 3.3, right? So is it 3.3 or 3.2? 3.3. Okay, so we have 3.3 multiplied by 0.6, right? So 3.3 multiplied by 0.6, that is 1.98 volts. Okay, and then V external, there's two places where there's a potential difference across VP and across this R2, right? So V external will be equals to VP plus the voltage that is dissipated by R2. So VP, we already know that it is 32. VP is 32. Now let's calculate the voltage dissipated by R2. So R2, the current that passes through R2 is 3.3 because that resistor is in series. And the resistance of R2 is 4. So let's add these. 32 plus 3.3 multiplied by 4. This is 45.2. So EMF will be equals to V internal 1.98 plus V external 45.2. So let me just add this. 45.2 plus 1.98. Okay, 45.2 plus 1.98. Yeah, this is equals to 47.18 volts. Right, that is the EMF of the battery. Yeah, obviously there's other ways of doing it, as it is quite clear. 8.3, bulb L1 burns out after a while. Assume that the resistance of bulb L2 remains constant. Will bulb L2 continue to glow after bulb L1 burns out? Choose from yes or no. Support your answer with a suitable calculation. So I'm thinking that it will continue to glow. So L1 burns out. First of all, we need to understand the consequence of L1 burning out. If L1 burns out, there's no current that is going to pass through here, right? There's no current that is going to pass down that path. So that path is essentially out of play. That is the consequence of L1 burning out, right? It's not gonna short circuit the circuit. Usually when bulbs burn out, they just act as a voltmeter of some sort, right? There's no current that passes anymore. It does not short circuit the circuit, right? So this path is gone. This path is gone. That path is gone. we can forget about that path. Okay, so even if that path is gone, there are some things that are still true. The internal resistance is still 0.6. The EMF is still 47.18. This is still true. What will change is IT, right? But R external, we can still calculate. R external will be L2 and R2, right? Because these two resistors are still in play. So R external is equals to, the resistance of R2 is 4. We don't have the resistance of L2, but we can use the information that is given there to calculate the resistance of L2, because the resistance remains the same, right? So we can still use that information. It's still relevant. So we have the power, we have the voltage. How do we calculate the resistance? P is equals to V squared over R. So R should be equals to V squared over P, right? So V is 32. So 32 squared over 48. This is equals to, so 32 squared, okay, 32. My calculator is in stats, so I cannot write divide, but I just fixed that. So 32 squared divided by 48, that is 21.3333 ohms. So this is the resistance of L2. So R external is going to be 4 plus 21.3333, right? What I'm about to conclude, we can conclude it without actually doing this calculation, but the question says let's calculate, so I'm just respecting that. So 25.3333 ohm is the new resistance. So what will happen to the total current? The total current will be close to the EMF, right, divided by R external 21.3333 plus R internal 0.6. This is coming from EMF is equals to IT R external. I'm actually doing this for myself to see if I'm doing it in the correct way. So IT, clearly it is equals to EMF divided by these two things. Okay, now I'm convinced that I'm doing it the correct way. So IT is equals to EMF 47.18 divided by the total resistance, which is 21.3333 plus 0.6. This is equals to 2.15. So the current, initially it was 3.3 ampere. Now the current is equals to 2.15. So the current is decreased. So even though the bulb will still glow, it will glow dimmer. Right, there we go. Question 8. Let's go to 9. Name the type of generator. Choose from AC or DC. Should be an easy question to answer, right? 9.1. This is DC. Why are we saying that? You can see that the induced current does not change direction, it stays in the same direction. If it goes down like this and forms a cos or sine graph, that would be an AC, alternating current. But in our case, we have a DC generator. That is 9.1. Let's take a look at 9.2. Say the energy conversion that takes place in this generator while it is in operation. So all generators, right? We have mechanical energy to electrical energy, right? That is what generators do. So if it was a motor, it will be electrical energy to mechanical. But because it is a generator, we have mechanical to electrical. We are generating electrical energy through mechanical and sometimes chemical. 9.2. What about 9.3? Give a reason why this generator is not suitable for the transmission of electricity over long distances. Right, that is because there's a lot of energy loss in a DC generator over long distances. That's one of the advantages that AC has over DC, in that you can use AC to transport the electricity over a long distance, right? But with DC, there's a lot of energy loss, right? 9.3, 9.4, calculate the frequency at which the coil rotates in this generator. So frequency is equals to 1 over period, right? So what is period? The amount of time it takes to complete one cycle, one wavelength. So you can see here that we have a half, and then this is another half. So from 0 to 0.02, that is a period, right? We have completed one cycle. So the frequency is going to be equal to 1 divided by 0.02. So 1 divided by 0.02, this is 50 hertz. So there we go. That is the period. 60. Oh, that is the frequency, not the period. 50 hertz. And then 9.5, define the term root mean square current. Well, I'm going to leave that to you. And then 9.6, calculate the root mean square current delivered by the generator. Well, let's go. We know that IRMS is equals to I max divided by square root of 2. Okay, so we can see here there that we have 1.2 divided by square root of 2. So let me just put that in my calculator. I'm getting 0.85 ampere. 9.6. What about 9.7? The graph below shows how the induced current varies with time after a change was made to the operation of the generator. Okay, so first things first, the Imax is no longer 1.2, but it is now 0.6, right? And then the period is no longer 0.02, it is now 0.04, right? So fully describe the change that was made. Okay, so let's do it like this. I'm going to comment on the period. I want you guys on the comments, on the comment section, to comment on the current that is induced. What do I say about the period? I'm going to say that the time taken to rotate the, what are we rotating? I'm seeing if we're given a specific word here, right? Well, the time taken to complete one cycle has been halved, right? That is why it takes twice as much time to complete one cycle, right? That's what we can see as far as the period is concerned. The rotation of the coil has been halved. That's why it takes twice as much time to complete one cycle. And what are you guys saying about the current induced? It was 1.2, now it is 0.6. Let's go. Which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2.65 times 10 to the minus 20 joules? There we go. Let's take a look at the equation statement. Red light, blue light, and green light are shown simultaneously on a sheet of potassium, as shown in the diagram below. Each color of light consists of a single frequency. Two maximum kinetic energies of the ejected electrons are possible. Two maximum kinetic energies of the ejected electrons are possible, namely 6.96 and 2.65 times 10 to the minus 20 joules. Each ejected electron has only one of these maximum kinetic energies. Okay, let's go back to our question. Which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2.65 times 10 to the minus 20 joules? So we need to understand what is going on. We need to think about what is going on before we can answer this question. So we have two maximum kinetic energies of the ejected electrons, right? But we have three lights that are being shown on the potassium sheet. So what does that mean when we have two maximum kinetic energies? It means that one of the lights is actually not ejecting electrons. Which one can it be between red, blue, and green? We need to go to our spectrum, right? Red, orange, yellow, ROIG, BIV. So red has the lowest frequency, right? So it's the one that is least likely to eject electrons compared to blue and green, as you can clearly see. So if we have only two maximum kinetic energies, it means that green and blue are ejecting electrons, but the red light is actually not ejecting electrons. So which color of the light is responsible for ejecting electrons that have a maximum kinetic energy of 2.65? So we then need to compare these kinetic energies to the lights that we have. Blue should be the one ejecting electrons with the most amount of energy. Okay, so between 2.65 and 6.96, 6.96 is greater, right? So it should be blue, it should be green that emits electrons with an energy of 2.65, and then blue will emit electrons with a kinetic energy which is greater than that of green, 6.96 in our case. So the answer to 10.2.1 is green, right? Green should emit electrons with less kinetic energy compared to blue. So that is 10.2.1. But in saying that, I've answered 10.2.2 as I'm explaining 10.2.1, right? Because that's what the question says. Explain the answer to question 10.2.1. So 10.2.3, the electrons with the maximum kinetic energy of 2.65 times 10 to the minus 20 joules are ejected by light that is a frequency of 5.85 times 10 to the power 14 hertz. Calculate the frequency of the light that ejected electrons with a maximum kinetic energy of 6.96 times 10 to the minus 20 joules. Okay, so what are we looking for? We are looking for the frequency of the light that emits electrons with a maximum kinetic energy. So EK max, that is equals to 6.96 times 10 to the minus 20 joules. So how can we solve this question? Well, we can just say that the energy is equals to the work function plus EK max. And then energy plus constant multiplied by the frequency, right? Planck's constant, as the name suggests, is a constant. So this will allow us to find the frequency. And then this will be equals to the work function plus the EK max, which is 6.96 times 10 to the minus 20. So there we go. This is the EK max. But you can see that we have a problem that is arising here. We don't have the frequency, but we also don't have the work function. But with the information that we're given, we can be able to calculate the work function for ourselves, right? Because we are given EK max and frequency of light, right, for one of the lights that are emitting electrons. So if we use that information, we can say the energy is equals to the work function plus EK max. We want to use this information so that we can find the work function, right, which will be equals to the energy minus EK max. So how are we going to find the energy? Planck's constant, 6.63 times 10 to the minus 34, multiplied by the frequency that is given, 5.85 times 10 to the power 14, minus the kinetic energy, 2.65 times 10 to the minus 20 joules. So the work function is going to be equals to, so let me put that in my calculator, 6.63 times 10 to the minus 34 multiplied by 5.85 times 10 to the power 14 minus 2.65 times 10 to the minus 20. This is giving me a work function of 3.6136 times 10 to the minus 19. What is the SI unit of work function? It is joules, right? So this is the work function. We can then substitute it back into this equation. So if we do that, we're going to have Planck's constant 6.63 times 10 to the minus 34 multiplied by the frequency. That's what we're interested in. So multiplied by F is equals to the work function 3.6136 times 10 to the minus 19 plus the EK max, not minus. So the EK max here is 6.96, right? So 6.96 times 10 to the minus 20. So 6.63 times 10 to the minus 34 multiplied by the frequency is going to be equals to 3.6136 times 10 to the minus 19 plus 6.96 times 10 to the minus 20. Right, let me put brackets here so that I can be 100% sure that my calculator is interpreting what I want to say the way I want to say it. 6.96 times 10 to the minus 20, 3.6136 times 10 to the minus 19. Okay, looks good. So here I'm getting 4.3096 times 10 to the minus 19. So let's divide both sides by the coefficient of f, right? So 4.3096 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. I'm getting a frequency of 6.5 times 10 to the power 14. So there we go. That is the answer to 10.2.3. Let's take a look at 10.2.4. So 10.2.4, the question is saying the intensity of the light is increased while the intensity of the red light is increased while the intensities of the blue and green light remain the same. What effect will this change have on the rate of electrons that are ejected? Choose from increase, decrease, or remain the same. So we have already deduced that the red light is not emitting any electrons. So what does that tell us? Even if we increase the intensity, it's not going to matter. If we increase the intensity of the red light, it's not going to matter. It's not going to affect the number of electrons that are being ejected, because the red light is not emitting any electrons, right? The energy that it carries is less than the work function. So even if we increase the intensity, it does not increase the number of electrons that are being ejected, and therefore increase the rate, right? So the answer yes remains the same. 10.2.4 remains the same. So 10.3, some of the atoms of a hot gas made up of a single element are in an excited state. The spectrum formed by the hot gas is observed on a screen in a darkened room. The spectrum consists of specific colored lines on a dark background. Specific colored lines on a dark background. 10.3.1, name the type of spectrum formed. So I'm asking you this question. Is this an emission spectrum or is it an absorption spectrum? Why do you say so? 10.3.2, explain the presence of the colored lines in the spectrum. Alright, so your answer to 10.3.1 is being explained by 10.3.2 essentially. So tell me, why are you saying it is an absorption spectrum? If you're saying it is emission, why are you saying so? There we go.